Hello, I'm Zhi-Qin from Shanghai Jiao University. In these short lectures, I will introduce phenomenon-driven understanding for deep learning. So we will cover the following topics. In the first, we will give an introduction to phenomenon-driven understanding. In the second, we will study the output space and introduce the low-frequency bias, which is called the frequency principle or spectrum bias. In the third, we will introduce the neurons in the same layer will tend to be similar during the training, which is called neuron condensation or neuron alignment. In the last part, we will give an introduction to this reasoning of transformer-based language model, which will also based on neuron condensation. So this is the first part, and we will give an introduction to this phenomenon-driven understanding. So what is the deep learning? This is a very simple framework for linear regression. We have a set of data, x and I, I and yi, and we use a very simple model to fit these data points. Definitely, this line cannot fit all the data perfectly. So we need to give a measure on how good this model can fit these data points. And we tune the parameter W and B to make this model best fit these data points. And finally, we will have some new data which is not used for training to examine if this model is good or not, which is called test error or generalization error. So I believe everyone knows this linear regression. The only difference between the linear regression and the neural network model, for simplicity, we can understand this way. Now we try to fit another set of data points, but they are not linearly, and so we cannot use linear function anymore. The most simplest way is to add a nonlinear activation function. So here's an example. But if you only need one, if you have only one neuron, meaning there is no summation here. For example, we take this reduce function as the activation function. The output will be restricted by this kind of shape. So we will have many neurons. We have this linear transformation, and then we have this nonlinear activation, and then we have another linear transformation. We have done this linear, nonlinear, and linear. We do many times, and then we take a summation of all these each component. Then we get a most simple neural network, which is called a two-layer neural network. One layer is W, the other layer is A. So we can also define the neural network recursively, use the output of L-1 layer as the input of the L layer. So we get this very normal neural network. But this normal neural network, it can power many amazing applications such as AlphaGo, AlphaFold, GPT-4, and so on. The only difference is we may change different form of weight or have some different specific settings. This looks like so simple neural network, but they can do so many amazing things. It makes us feel very strange. How to understand this? They are so powerful so that many people argue that we may not need any theory. It's so powerful. Why bother with study theory? So I will give some example why we need a theory for deep learning. So for the first law of thermodynamics, it simply says the conservation of energy. Although we may not use this law to build any machine, but it can help us to avoid wasting energy. For example, it tells us that the first kind of perpetual motion machine is impossible. We don't need to pay any energy money to build such machine. From the chemistry, we know there was a period of alchemy. People try to transfer copper into gold, but we know it's only in a change of electrons, but not nuclear. So it's not impossible by only doing these chemistry things. Although, as far as we can know about this, we can avoid a lot of energy, and there indeed a lot of money and energy are wasted in history. On the other hand, we know that the wood carbon can be transformed into diamond because they basically have the same atoms. And once we have appropriate conditions, such as high temperature or pressure, this transformation can be made possibly. So once we understand a system, we know its limitation, and we can avoid wasting too much time on doing something impossible, and we also can and try hard to find some appropriate conditions for something very difficult. So similarly, for deep neural network, if we understand it well, we can know that what the deep neural networks are good at or what is difficult for them. For example, we will mention that high frequency is difficult for neural network. So we will start with a very popular phenomenon, which is over parameterization partial on generalization. So let me ask a question, very simple question. Is neural network really so complex? The answer actually is very also simple. Yes, neural network is complex. Even you have only two-layer neural networks, once you have sufficient large width, meaning you have as many neurons as you want, then you can fit any continuous function by arbitrary accuracy. So it's very complex. It can approximate almost any continuous function. But if a model is very complex, what's the disaster? The traditional learning theories tells us that if you have a model with very large complexity, you will highly possible have overfitted data and bad generalization error. Here's an example. If you have a very simple function to classify these two types of data, the circle and star, then you will not be able to do it good because this model is not complex enough. But if you use a very complex data function, you definitely can classify all the training data very, very well. Even for data like this, it possibly be a noise, but you can fit this noise also very well. But we don't have this this classification function usually, because we know that if we sample another data points, such as we sample another data points in here, then usually we assign this point as a star, but this classification will classify this data points as circle. So this will make it the model generalized very bad. So traditional theory tells us this: if you increase the model complexity, the error of training samples will decrease. But after some point, the error of test data points will increase, and you will have this generalization gap. So a very simple tip from this traditional learning theory is do not make your model too complex. And there are also a lot of examples. Here's an example. Van Neumann said, give me 4 parameters and I can fit an element. Give me one more, I can make the elephant move. So in 2004, this paper really makes this happen. This story tries to tell us that if you have enough parameters, you can almost fit anything. And there's also a very famous principle that is called Occam's razor, meaning no more things should be presumed to exist than we are absolutely necessary. That is, the fewer assumptions an explanation of a phenomenon depends on, the better the explanation. So many scientists, when they are trying to build a model, simplicity is one of the most key ingredients. So what about the neural networks? Now we can take a look at very simple examples of one-dimensional data interpolation. Suppose we have these four data points, and we use neural networks of different layers, from 2 layers to 12 layers. And you can see the neural network can easily fit all these 5 data points, but it looks like they don't have much fluctuations. So the question is, can the neural network fit the data with some fluctuation curve? Yes, they can. If we assign more data, for example, we assign data here, assign data here, here, and here, and also with these original 5 data points, now you have 9 data points, and the neural network can fit these 9 data points very well. Definitely, there are also an interpretation of these 5 data points, but they are much more oscillated. But usually, if you don't have any other things, they always use a very much flat curve to interpolate these data points. So it's very strange. The neural network can fit the data points with very oscillated curve, but they don't. So this is another example I used four hidden layers with 5 neurons in each layer, and use tinge activation function to fit these data points. You can see it's very smooth. And the question is, the number of parameters, they are much larger than the number of data points. But why it doesn't overfit? It seems have this difference with this traditional learning theory. So in 2026, there was a paper. They used a network model with almost with more than 1.6 million parameters to feed the Zhi-Qin data to classify 60,000 images into 10 classes. Either you use some localization like random crop or weight decay, the neural network can always classify training images with 100% accuracy. Even they shuffle the labels for the training data, they can still have this 100% accuracy, meaning this model is very large. So this model has very large number of parameters, which is much larger than the number of training data. And the random guess of the test samples is almost 10%. And we can see that for this normal training, the test accuracy is much larger than the random guess, which is almost close to this 90%. So meaning the neural network, although it has the number of parameters much larger than the number of training data, but it can still generalize very well. This is a puzzle. It's different from what the traditional learning theory tells us, or the traditional trouble of complex model may ignore deep learning. Actually, this problem is first raised by Leo Bremen in 1995 after he referring papers for NIPS, which is called neural IPS now. He proposed several questions, and the first one is, why don't heavily parameterized neural networks overfit the data? I believe this is a very interesting problem. It has some it hints some direction to study the neural network from the number of parameters, which is much better than question like this: why the neural network is so powerful? This question definitely is important, but it doesn't give us any information of how to study neural networks. So the number of neural parameters definitely is very important, and he points out. So the following question is, what is the effective number of parameters? There are so many parameters, but does each parameter take some important roles or plays an important role in the neural network? We don't know. Maybe they are redundant. So what is the effective number of parameters? And then also some training issue. Why doesn't the backpropagation head for poor local minimum? And when should one stop backpropagation and use the current parameters? Very interestingly, he also there was a note or remark in his paper. It says mathematical theory is not critical to the development of machine learning, but scientific inquiry is. To my understanding, I actually quite agree with this because as the neural network is so complex, it's almost impossible to use a very simple formula to explain everything. One way to study this complex system, such as natural system, we usually try to observe a lot of phenomena and then try to summarize some important laws, use these laws to guide us to use this system or to use these laws to propose some mathematical theory. So that is the way of how scientific inquiry improve our understanding on natural system. And this phenomenon has inspired a series of subsequent works. The most two important phenomena we will introduce in this short course will be frequency principle and condensation. For the first phenomenon called frequency principle, you also call spectrum bias or frequency bias. We have recently an overview paper for this phenomenon. So to understand this phenomenon, we will start from one-dimensional fitting. We pick a target function such as this red curve. It has some multiple discontinuity. So the blue curve is the output of neural network initially. They are very different. So we will use gradient descent based methods like ADAM or SGD and so on to fit this this target function. Now let's take a look at this movie and to see how the network fit the curve as the training goes on. Initially, you will start to capture the landscape of the target function, and after some training, you will learn more and more details. And to quantitatively understand how this training process goes on, we can use some more quantity to capture this landscape and detail, which is frequency. So this red curve is the Fourier transform of your target function. And this blue one is for the neural network. And the x-axis is the frequency, and y-axis is the amplitude. It has many frequency peaks because the target function we selected has many discontinuity. Now also, we have this training process goes on, and we can see the neural network first fit the first frequency peak, and you will learn more and more frequencies. Although this very simple experiment may not sufficient to support our claim that the neural network learns from low to high frequency, but it inspires us to design more and more complex experiments to show that this frequency principle is very common. Okay, the second phenomenon is called neuron condensation or neuron alignment. And this is an ongoing work, and there are still many works starting on this phenomenon. So to give you a very simple understanding of this phenomenon, we do not show you very exact experiments, but some toy example. So in this example, we have 5 neurons, meaning so if you have an input X, I will perform this transformation, linear transformation, and then this nonlinear, and also have some weight. And then we have 5 different neurons. There's WIs, I from 1 to 5. They are all different at the initial stage before training. But after training, we found a very interesting phenomenon. These neurons will be clustered. The first 2 neurons, they will group together, and the last 3 neurons, they also group together. Meaning the weight of the first 2 neurons, they are the same. And the weight for the last 3 neurons, they are also the same. So after the training, this neural network actually can be equivalent to a network of only two neurons, meaning we can combine the first two neurons together and also can combine the last three neurons together. So this neural network is equivalent to a network of only two neurons. So previously we have mentioned about the neural network with many parameters, but actually after training, the effective number of parameters, they are quite small. So these two phenomena, they are very simple, but they have a lot of advantages. For example, we can have rigorous theoretical analysis. They can inspire the more efficient algorithms. They're simple, but they can help us explain the over-parameterization puzzle. So for traditional methods, if you have the number of parameters larger than the number of samples, you can easily overfit the data points with high frequency curve or large complexity curve. But for neural networks, it can bias towards a simple function. Why? Because it have this implicit bias of low frequency and also try to equivalent to small effective neural number. So you can easily use a very flat curve to interpolate these data points. So there are many interesting phenomena in the deep learning community. So we will select some to introduce. So this phenomenon is called adjustability. To understand this, let me first give you some very simple, intuitive example of the learning rate and the stability of learning. So for the optimization on this quadratic loss function, if you choose a very small learning rate, you will use many steps to converge. But if you choose a very large learning rate, although the direction is right from this point to this minimization point, but the step size is very large, so you will cross this minimum point to the other side, and the loss also increases once its distance from the distance from here to the minimum point is larger than the original point to the minimum point. And during the training, the loss will increase. So this is an unstable case. But if you choose some learning schedule very appropriate, meaning it's not too small or not too large, it will reach the minimum with much smaller steps. So let's give an intuitive mathematical deduction for understanding their relation. Consider loss function of quadratic function. This theta is your parameter. This lambda is the curvature on the second order derivative. The gradient descent is very simple. The parameter at t plus 1 equals the 1 at t minus the learning rate times the gradient. Since this is a quadratic function, this gradient equals to lambda theta. So we can take out of this theta and get this one is 1 minus eta times lambda. And to make the loss smaller, so the distance to this minimum point, 0 here, should be smaller and smaller. So the absolute value of theta t plus 1 should be smaller than theta t. And then you can get this 1 minus eta lambda smaller than 1. And finally, you can get lambda should be smaller than 2 over eta. So if you are doing this optimization process in a non-convex loss function, there are a lot of different local minimum and different this curvature. Which curvature you should select? To get a stable training, the training should be in a region that this curvature should be smaller than 2 over your learning rate. And for high dimensional case, this lambda actually is the eigenvalue of Hessian matrix. Hessian is the second order derivative, or you can consider as the curvature or flatness, sharpness of this loss landscape. Very interestingly, it seems that the training of deep neural networks like to play at the very edge of stability. So here's an example, several examples. You can choose different learning rate and use different data set to run the neural networks. The prediction age of stability is 2 over eta. So except for this very simple example, you can see for most case, the prediction in this case is 40, and the lambda or the maximum, the largest eigenvalue of hashing equals to almost 40, equals to this 2 over eta. And we know that if you select a place is curvature or its second order derivative is larger than 40, it will start to oscillate. Right, so it stays a very, very critical or very dangerous place. So for other experiments, you can see they are all very close to this 2 over eta. So on the other hand, if you want to choose a training trajectory or training place that is much more flat, the curvature is smaller, then you can also tune this learning rate, make this learning rate larger. So this second order derivative will be smaller, and finally it will stay in place with small curvature. So we can use this learning rate to select a flat or sharp minimum, and we will introduce more about this sharp and flat concept in the following session. We will introduce another phenomenon of flat solution and sharp solution. This is a very famous paper to study how batch size will affect the learning. And they found that different batch size will find minimum with different sharpness. Here's a very intuitive example to understand how sharpness affects generalization. So consider this is the parameter space, and this is the loss function fx. And for the training data and test data, you can have different loss function, because usually we have this noise or some other different factors we don't consider in, so they have different value, or they have slightly difference. So this dashed curve is the loss function of test data points. They are slightly different. And if you find a minimum in here, although it is different from the minimum of test function, they are different. But since here is very flat, so the loss from the test data points is also very small because it's very flat. But if you choose, if the minimization finds the minimum of this sharp minimum, although there are also not so much difference in this parameter space, but since here is very sharp, so the test loss function here is very, very large. So definitely the generalization for these two parameters are very different. This flat one is very small, but this sharp one is very large. And they try to study if this is the key to different generalization of using different batch size. So they test the different experiments with different batch size. The batch size means we use in each training step we randomly select a batch of samples to compute this loss function. So we don't select all the samples, then it's equivalent to add some noise to this full sample loss. And one of key factor is how many samples we select for each training. So this small batch is denoted by SB, and large batch is denoted by LB, and they use different experiments to show that for the training accuracy, this small batch or large batch, they can always achieve almost 100% accuracy. But now the key thing is this testing accuracy. They found that very interestingly, the accuracy of a small batch size consistently larger than the accuracy of large batch size. So here, small batch means 256 data points in each batch, and the large batch means 10%. So for sigma 10% may be equivalent to 5,000 or 6,000. So it's 20 times of this small batch. The difference is also very significantly is have like 2 or 3% increase, or maybe this is 6%. So it's very significantly. So they study the loss landscape of different minimum. So this zero means the small batch size, the parameter they found by the small batch training, and one means the minimum of large batch size. So in the parameter space, you have 2 points. And once you have 2 points, you can connect these 2 points and get a line, right? And in each line, you have this interpolated parameters value. So you can also use this value to compute the loss. You can see that for this small batch minimum, its level is very flat, meaning that you have this small perturbation, the loss function do not increase much. This is the loss function, the red curve for the solid curve for training data, and the dashed curve for the tested data. And this is the accuracy. And you can find that very similarly to the previous intuitive understanding for the small batch with beta generalization. It's flat. It's more flat, but for this minimum with worse generalization, it's more sharp. And this phenomenon is observed in many different situations. So this is quite general and a very good picture to help us to understand how the flatness affects the generalization. The next phenomenon is about noise structure in SGD, and we will continue to talk about what SGD can help generalization. The spatial noise structure is very related to this loss landscape, so it can help the neural network to find some more spatial minimum. This is another understanding of SGD. We know that for the SGD, we compute the loss function. Usually we compute with all samples, but in SGD, we only compute some random selected batch, meaning we don't use all the samples to compute this function. So this is equivalent to add some noise to this full batch gradient descent training. And this noise is very spatial, and the covariance is you can compute it. It's not a homogeneous one. And now we can also compare this stochastic gradient descent with another stochastic dynamics, which is called Langevin dynamics. Meanings we have this full gradient descent here, but the noise we use is a very spatial one. We use a homogeneous one, meaning in each direction the noise magnitude or variance is the same. And there are also different kind of this Langevin gradient dynamics. But now we can take a look at the experiments. We can not go into so much details. So they perform experiments on CIFAR10 with VGG11 with different training dynamics. This is the test accuracy. You can see that for stochastic gradient descent, it has the most, it's the highest accuracy compared with other stochastic training dynamics. So this is another experiment. So this tells us that the spatial noise structure for stochastic gradient descent enhance the model generalization. But how spatial of the noise? Let's study it with the flatness of the loss landscape. So how we define the flatness of curve? So suppose this is the minimum here, fidelity is the minimum here. And now we consider if we want to find another place that the loss is times the loss is E times L0 here. So this is a fixed increase. And if in the parameter space you need to go further to reach this increase, then it will be more flat. So this is the basic idea. So you can define this point by this way. This theta t is the minimum point, and you will go in this direction, meaning the flatness in a specific direction. Go in this direction with the distance delta theta. And this delta theta will be used as the flatness for this direction. So if this delta theta is larger, meaning you need to go further. For example, this green curve is flatter than this blue curve. So this is the basic idea to define this flatness in different direction, this pi here. And the result is very interesting is they found they can also compute the noise variance in this direction. They found that if the network, if in the loss landscape, if in each direction, each point is one direction. So they found if in this direction it's more flat or it's more sharp, then the noise will be more larger and the fluctuation will be larger. Meaning that, consider in this way, if you have this loss landscape very, very sharp, and if you have this very flat curve, and you have a lot of noise, very large noise, then what will happen? You will sometime, after some training time, you will, with high possibility, you will jump into this place because this is too sharp and the noise is too large. You cannot stably stay here, so you will jump to a flat place. Basically, this picture or this experiments tells us that in a more sharp place, the noise will be larger, and in flatter place, the noise is small, so you will highly possibly stay in this flat region. So the SGD noise is very special. It's different in the noise magnitude is different at different direction, depends on this loss landscape structure. Intuitively, we can understand it's also reasonable because the loss function is computed by these samples, and this noise is also induced by we don't compute all samples, so they are highly related. But while they have this relation, we may need more theoretical understandings. The next phenomenon we want to introduce is double descent. So in traditional learning theory, we anticipated that as the increasing of model complexity, the training error will continuously decreasing. But for the test error, the error will first decrease and then increase. That is so-called overfit. The key reason is the model is too complex. It can learn everything. But for deep learning or for some other methods like a kernel method, a new phenomenon called double descent is found. This is an experiment from 2019 paper which first reported this phenomenon. It's an experiment of fully connected neural network performed on a mixed dataset, which is a very, very simple task. As the number of parameters increase, which can be regarded as the complexity of the model, the training error continuously decreases. However, for the test L, it first decreases, that is expected, and then it increases. That is also expected. because of this overfit. However, as the neural network continues goes on, we can see the tensor L decrease again. And there are two stages of decreasing. So this phenomenon is called double descent. This phenomenon has a stark difference from the traditional learning theory. So it calls a lot of attention. In 2021, OpenAI has a paper about this double descent. They performed extensive experiments. And very interestingly, we can see the label noise is a very important signal. What is label noise? That is, we have some noise on the output label. For example, for the image classification task, we may randomly shuffle a portion of samples, and that is regarded to add some label noise. So here's an experiment. If we don't have any label noise, that is a regional data set. You barely see this double descent. In this experiment, you almost cannot see it. Okay, now if we add label noise, for example, if we add 20% label noise, you can see there is a clear double descent phenomenon. Also for this one, this is for CIFAR 100 and for CIFAR 10. So we can see that label noise looks like very critical to practical data sets. Lottery ticket is also a very interesting phenomenon. It says that in the neural network, we may have a subnetwork which is very lucky. How lucky it is. So we random initialize the neural network with for each parameter with randomly sample its value from some Gaussian distribution or uniform distribution. Then we train the neural network. After the training, some parameters, their magnitude are very, very small, so we can just prune it and to 0. And the accuracy almost does not change. Oh, this is a very normal prune process. But the interesting thing is as following. So once we mark those parameters will be pruned, we mark the index, and we go back to the initial stage. In the initial, after initialization, we don't change the initialization anymore. Their value are fixed after the initialization. And we know some parameters will be useless after training. So in this sense, we just do not train them from the first beginning. For example, after training, this one will be neglected. Okay, so we actually don't train this parameter from the first beginning. So we only train a small portion of all parameters, and then we can get after training, the neural net we get, the accuracy is very close to the training of all parameters. But one key thing is we only initialize this neural network one time. If once you mark this parameter and go back to the initial state and you reinitialize it, if you initialize it again, then everything change. Okay, this mark will be meaningless. So remember, we only initialize the neural network one time, and after this initialization, we trained to the final stage, and we find that some parameter is very small, so we mark them and we only retrain it, but only train the neural network with those will be used in the previous training. So meanings there is a subnetwork. Once we only train this subnetwork, after initialization, we have a subnetwork. And even we only train this subnetwork is equivalent to train all the parameters. So suppose we can find some algorithm that can identify these parameters that need to be trained at a very, very early stage, actually we can save a lot of energy or set of computation, a lot of computation to train this neural network. So now let's take a look of the performance of such kind of subnetwork. So this 100% means you train all the 100% parameters. 50.3 means you only trained 50% of 51% of parameters. Of course, you identify it by first give a full training, and you can see that the accuracy actually is slightly better. And if you use this 21% parameter for training, you can get a better accuracy. You can get a very consistent result for different experiments. But if you reinitialize after you select like 50% and you completely reinitialize it, you can see the result actually is very bad. Okay, it's not good, not good. So to find this lottery ticket, it's not an easy one. So you need some lucky. So it's called lottery ticket. But there's also some interesting work try to find this lottery ticket in a very urge training, so you can still save the training computation. The next phenomenon we want to introduce is called grokking. Before that, let's revisit what we might think the training loss and the test loss will be here. Here's a typical example. During the training loss indicated by this orange line will continuously decrease, and so is the test loss. And we can see that they have a similar tendency, or in some cases, this test loss might increase at the end of training stage. That is overfitting. And after training, we can see there's a gap here. That is because the generalization gap exists. However, here's an example that uses transformer neural network to perform a modular division task. That is performed by x is divided by y, and then perform this modular on p. During the training loss will continuously decrease. That is what we expected. However, for the test data indicated by this green line, it first decrease and then it increase in a very significant value. And after some training steps, it starts to decrease. So if we take a look at the accuracy, we can see that the accuracy of training data will continue to increase. However, for the test data set or validation data set, it stays at a very low accuracy until some steps, before which the test accuracy already achieved 100% accuracy. So that is called grokking, because after some step, seems the neural network suddenly have a transition of its intelligence. It learns how to perform this modular division on new data set. There are many works working on this grokking understanding. Here's an example. So in this example, we use one-dimensional data set to understand from one aspect called frequency perspective to understand why grokking can happen. So in this example, the target is a function of sin 6x. It's a highly oscillated curve. In the first, we sampled 10,000 evenly spaced points in a range from -pi to pi. And then we sort the samples by this distance. That is, we want to find samples that is very close to this sin x. So we sampled S data set data points. And for an experiment of n training data points, the left n minus s data will be uniformly and randomly selected from the complete training data set of this 10,000 evenly spaced data set. So by this sampling method, we know although we sampled from sun 6x from target function, but there is a significant portion of data very close to this sun x. Take an example. So these blue star points are the sample data points. And they are sampled from sun 6x. However, because we use a very spatial sampling strategy, somehow it looks like sun x in the first beginning. So during the training, these green data points and the red curve is the output of neural network. At the first beginning, they are different from the training data. But after some training steps, it learns like a sun x function. That is because the training data has shown some false low frequency that is called aliasing effect. And the neural network have a frequencies principle that is neural network tend to learn low frequency first. So to explain the data, the neural network first learns an output very similar to sun x. However, if you really want to capture all data points, definitely there is no noise, so you have to learn this sun 6x function. So after the training, the neural network output very similar to this sun 6 function. So during this training, we can see that this color indicates how much portion we select from this random data sets. So if you consider this, the first line here, means most data are selected from those very close to sun x function. So it will first learn the sun x function, and since sun x is very different from sun 6x, so the test error will increase during the first learning stage. However, if all the data sets are sampled from randomly uniformly data points, then the test loss will continue to decrease, but there is no growing phenomenon. So by using this very simple trick, we can understand that because there is a false frequency during the end of training data points. So the neural network will first capture this false low frequency that will induce the increasement of test error. Another phenomenon we want to introduce is neuron collapse. So to introduce this phenomenon, we need to define the feature in this phenomenon. Consider a neural network. This is the output layer. This is the last hidden layer. We define that the output of the last hidden layer as the feature. So for each input, you can obtain a feature. Consider a classification task. These dots or these tiny balls, they are features of each one input. So each ball will correspond to one input. And different color here, the different color here means they come from different classes. The interesting thing is the feature of the last hidden layer, the output feature. From the same class, if the image belongs to the same class, the feature will be condensed or collapsed to almost the same one point. And these points are very interestingly, that is, the distance of their mean is separated as much as they can. So consider here, this big ball is the average of the balls, tiny balls that belongs to this deep blue class. And this light blue one is also the average of the features of these balls that also belongs to the same class. So we can see that they are very close to this red one, this red type one. Okay, and this red type one is called simplex equiangular tight frame. The name comes from this property that these vectors, they are separated in the space as much as they can. So interestingly, that the neural network try to separate, not just to separate the inputs, but also to separate them as much as they can. And because the input that from the same class, their output feature of the last hidden layer almost condensed into one vector, so they call this neuron collapse. The next phenomenon we want to introduce is mode connectivity. As we know that the neural network usually has a lot of parameters, so the loss function, which is a function of all these variables, is very high dimensional and is also very complex. In 2019, a very interesting paper that they show an image that you can provide, any image you can provide. It seems you can always find a two-dimensional cross-section in a loss landscape that is almost exactly to the image you provide. Suppose you provide an image of bat, and you try to find a two-dimension. In these two dimensions, the loss function looks like the bat. So the color here means the loss value. And these two directions are the directions that found by optimization process. So there are also other examples that the cross-section of loss landscape can be almost any pattern, so it's very complex. However, the minimum in the loss landscape seems have some underlying connection. So here are three global minimum they found on this experiment of a ResNet 164 or C500. If you simply connected any two minimum, you can see the loss will increase at some middle stage and then decrease again to this the other minimum. However, it seems you can always find a path that is not straight, connects these two global minimum or any two global minimum, and the loss on this path, they are almost constant, meaning all points in this path are very close to global minimum. So it seems all global minimum are connected. So this property is called mode connectivity. It's very interesting and very hard to explain why this so complex model can have this property. We will also introduce some phenomena about large language model. Here is the first one called in-context learning. Consider you are training a neural network or language model that has never been used to or never been trained to perform such task. Give a review and you need to give a sentiment. But now we can do this task in this way. Suppose we have this data set. We have text and also its label. So we reorganize this each data point into this way: review, and then a text and sentiment, the label, like positive, negative, or neutral. And then we give CAD demonstration examples in this format: review and sentiment. And in last query, we only give this review, but leave the result of sentiment blank. And use this as an input to the model. You will find that the neural network can perform such task very well. But such task was never seen during the training, meaning the neural network learns from the context. So we can imagine a lot of things. We may not have seen anything, we may not see things during the training, but to ask a neural network to do such task, we can first give some example that is very similar to our humankind. So here's another example. Suppose you want to do an image segment of a horse here. And how to do it? You may give an query image, and you give an image here, and the output is you just segment the horse. And then you give an image of another horse and leave the blank as an output, asking the neuron to give the output. So the neural network, so in this way, you give a text prompt, then give an image, then give an output, and also give another image. You ask the neuron to do the next token prediction, and you will give out this the output on image that segment of horse. So a lot of tasks we may not know how to do it, but we can give a lot of examples, and this is a very powerful ability because during the training we don't need to see every task, but we can do it after training. That this way is very powerful to generalize to more tasks. It's not simply a data generalization, it's a task generalization, and it's learning without any fine-tuning, so it's very convenient. The second phenomenon I think is very interesting is the chain of thought. Of course, there are many other phenomena, but we will not go into too much. So this chain of thought is also very similar to humankind. So consider we are going to do a math problem. And here's an example. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? The answer is 11. Now we give the question. The cafeteria had 23 apples. If they use a 20 to make lunch and bought 6 more, how many apples do they have? Now model output, the answer is 27. So obviously it's wrong. But now if we change the prompt as a way of chain of thought. So the answer to the first question now is Roger started with 5 balls, 2 cans of 3 tennis balls each is 6 tennis balls. 5 plus 6 is 11. So the answer is 11. So there is a roadmap of how we solve this problem. So now we give the same questions of the second one. Now the model output is the cafeteria had 23 apples originally. They used the 20 to make lunch. So they had 23 minus 20 equals to 3. Now they bought 6 more apples. So they have 3 plus 6 equals 9. The answer is 9. So now by using this chain of thoughts, we can enable large language model to tackle complex arithmetic, common sense, and symbolic reasoning tasks. So this is a very interesting trick. And there are some theories have been done to understand why this chain of thought can improve the performance of language model. One of the key reasons is by using the chain of thought, you can reuse the model multiple times. So you can increase the expressiveness of the model in the other way by not using increasing the number of parameters, but by using the models multiple times. So the large language model is very interesting, and there are many other phenomena. And we will go into language model in our fourth topic. That will be the end of the first introduction.